is assignment 4, part 1, task 1. And here we can see the library, library of ERC20 and ownable tool. Ownable and the create contract, my custom token is inherited from ERC20 and ownable. It adds functions that we will see in the future. I will show it. And I create a token by ERC20 and I create a function. Owner can call this function. Okay, and runs this contract, and we will deploy this contract. Deploy address, owner address, transact, it's working. Then we open deploy contracts, and we will first mint. We will send to us tokens. We need to write a big number. Okay, transact. Okay, it's transact, and we will check the balance of this address, our address. It's saying that we have that many tokens, and the proof we need to write other address like this, and okay, also we need to write a big number, transact, it's working. And we also need to write a as link. I use as address. It's working perfectly, and yes, it's also working perfectly. So our code with ERC20 is working. Like and subscribe.
We begin in the deploy and run transaction tab, where our environment is set to the Remix London VM. First, we select our contract named MyNFT and click deploy. The transaction is immediately processed on the local blockchain. Once confirmed, the deployed contract appears in the deployed contracts section, exposing its public functions and state variables. Before minting, we can verify the initial state by calling the name and symbol functions. We see the metadata initialized by the constructor. We also check the next token ID, which currently sits at 0, indicating no tokens have been issued yet. To mint an NFT, we navigate to the Save Mint function. We provide two parameters: the recipient wallet and token URI. After clicking transact, the VM executes the logic, updates the mapping, and emits a transfer event. By expanding the transaction logs in the terminal, we can inspect the execution details. Here we see the decoded input, the gas cost, and the logs confirming that token ID 0 was successfully assigned to the specific address. Finally, we verify the results. Calling next token ID now returns 1, and querying token URI for ID 0 confirms the metadata link is correctly stored on chain. The balance of the recipient address has also been updated to reflect ownership of the new asset. This workflow illustrates the seamless cycle of deploying, minting, and verifying non-fungible tokens within a local development environment.
In this code, first I deploy the contract and mint some tokens to the owners so I can run transfer test. Then I verify that minting increases a user's balance and updates the total supply properly. And I test transfers to make sure tokens move correctly and that the transfer event is emitted. After that, I check the approval and transfer from logic. to confirm allowances work as expected. And finally, I test failure cases to ensure the contract reverse when there is not enough balance, not enough allowance, or when a non-owner tries to mine tokens. And I can show these tables. It's here we can see all is correct, and in my custom token approved transfer from it's all working and it's all showing it's for us. Okay, and it's a second code ERC721, and it deploys the contract means NFT and verifies that mining emits the contract the correct answer event. It confirms that ownership and token URI are stored and returned correctly. The test also validates approval logic, like approve, transfer from, set approval for all, and certain tokens can be transferred only with proper authorization. Finally, it checks that the contact correctly reverts when a non-owner tries to mint or when a non-existent token is queried. You can see it, and it's a smart contract of this. And now I will show the table. Okay, it's all table. You can see it. It's correct. It's all correct. Yes, it's approved mint NFT. Set approval for all and transfer from how I was said before.
We begin on the main dashboard where the user has already connected their MetaMask wallet. In the ERC20 section we can see the current balance for my token. To demonstrate the transfer, we have entered the recipient address and a specific token amount. Once the transaction is processed, the interface provides a real-time success message and the unique transaction hash. We will now copy this hash and go to the address scan explorer. We can see the status of success and transfer of 0.8 zeros and 3 MTK from our connected wallet to the recipient.
It's part 4. It's a vulnerable contract. It has a problem part here. In the fixed, I have fixed it and it doesn't have any problem. We can check it here. I will show this table. Yes, you can see it. It's a fixed, it's a vulnerable, and here we can see in the vulnerable smart contract, the attacker take all monies. In the fixed, they doesn't take any monies.
The contract is built around two primary data structures: a candidate struct, which stores name and current vote count for each participant, and the voters mapping, which tracks whether a specific wallet address has already cast a vote. The contract also uses only owner modifier. This ensures that only the administrator who deployed the contract has the permission to register new candidates. You can see here in the deployed contract section that we now have access to administrative functions. As the admin, I will now add our candidate Alhan for ID 1 and Nurbak for ID 2. And the candidate's information is permanently stored in the contract's memory. Now let's give some votes for Alhan, like 1 vote, and for Nurbak 3 votes. To wrap by calling the getResults function for ID1, the contract returns the name Alhan and vote for count 1. And this entire process from registration to tallying is fully decentralized, transparent, and immutable. This is the logic flow. You will see how we manage two primary roles, the admin and the user. The process begins with the admin. Admin can add candidates that are stored in a candidate list, and we have a boolean mapping as a has voted status to track whether a specific validator has already participated. Now let's look at the user flow. When a user decides to participate, they call the function vote for a specific candidate ID. The system asks for is the candidate valid and has this address already voted. If the mapping shows the user has already voted, the transaction is reverted to prevent double voting. However, if the mapping is false, the system proceeds. It updates the user's status to true and increments the vote count for the chosen candidates in the registry. Finally, the system allows for public transparency. Any participant can call the view results function.